I was asked to give lectures. Is it too loud? Should I move this down? I hear some feedback. Okay, we'll try it. I was asked to give some lectures. Actually, I wasn't instructed at all in what to talk about, so I had to think of something myself. And I decided to try to give some kind of introduction to entanglement in quantum field theories and in holography. So let me try to be concrete just to set the stage what I'm talking about. So I have a quantum field theory in some number of dimensions, and let's say that this is on some space. This is the space the quantum field theory is on, and it's in some state rho, which could be pure state, could be the ground state, or some, there could be a particle flying through, could be a mixed state like a thermal state or something like that. And just as some of the other speakers have been doing, we're going to divide it up, and we're going to have some spatial region, which I'll call A. The boundary, so A is a spatial region. Its boundary is called the entangling surface in this context. And what I'm interested in is understanding, and then we have the rest of the space, a complement. I'm interested in understanding to what extent A and A complement are entangled. Actually, that question is really appropriate if the full system is pure. So I'm going to be a little bit more general. I'm going to allow rho to be mixed. If it was pure, the way we would quantify that would be via an entanglement entropy. And I'm going to continue to call that quantity the entanglement entropy. That quantity is the von Neumann entropy of the reduced density matrix. So we have rho sub A. Oh, let me say one thing first, actually, prior to that. So I assume I have some local quantum field theory, and that means, in particular, that the Hilbert space can be considered, the Hilbert space for the full system can be considered as a tensor product of the Hilbert space for the region A and its complement. And the basic justification for that is simply that we know that operators inside A, we know that in quantum field theory, operators at space-like separation commute with each other, so any operator inside A commutes with any operator in A complement. And so therefore it makes sense, it stands to reason, that the Hilbert space would factorize in this way. Now this is a fiction. It's not, so there are subtleties associated with this equation, which I'm just not going to talk about. If you want, you can ask about them, we can talk about it, but I'm going to skip over that. Okay. So if you want to sound sophisticated, you can always, and a speaker is giving a talk on entanglement entropy in field theory, you can always question them about this equation, and then you'll sound really smart and sophisticated. But for our purposes, we're going to pretend this, and this allows us to define, is it okay if I write down here? Let me try it and see if anything happens. The reduced density matrix, which is the effective state for an observer who has access only to the region A, and its entropy, which is the von Neumann entropy, which is called the entanglement entropy. And this quantity quantifies, if rho is pure, then this quantity, S of A, quantifies the amount of entanglement between A and A complement. If rho is not pure, it doesn't, but we still call it that. Okay, another thing you can do if you want to sound sophisticated, again, is you can object to this terminology, which is a terrible terminology. Okay, so this is going to be the subject of the lecture. And the point being, as I'll try to illustrate, that this quantity reveals an enormous amount of physics about the underlying field theory, about the state it's in, and so on. a lot of interesting physics. That's something that has been understood over the last few decades very gradually. I'm only going to scratch the surface, hence intro. So it'll be a bit skeletal, and it'll be in two parts. So first I'm going to talk about field theories in general, and then I'm going to switch to holography, and that'll require me, given the audience, I think, to give some kind of, again, skeletal introduction to holography. Before going on, let me say, so I'm not I understand this is a condensed matter school. I'm not a condensed matter physicist, so you could ask, why am I here? Excellent question. I think the answer is that entanglement entropies are one of these subjects where you can really wax lyrical about, interdisciplinarity and intellectual cross-fertilization and so on, because it's something where high-energy theorists, such as myself, and condensed matter theorists, and also quantum information theorists have learned an enormous amount from each other over the past, on this subject, let's say roughly 15 years. And I think high-energy theorists have a little bit of bragging rights here, because one of the ways that thinking about entanglement entropies entered into condensed matter theory was from high-energy physics. And where did it come from in high-energy physics? It originally came from trying to understand black holes. Okay, so basically, people were trying to understand black hole entropy, and that made them think about entanglement entropy in quantum field theory. And then more recently, it's come back full circle, and thinking about entanglement entropy in quantum field theory has led to new results in understanding gravity, quantum gravity, and black hole entropy. So let me tell a little bit about the history. So where this subject started from a high-energy theorist perspective was the discovery by Bekenstein and Hawking in the 70s that black holes have entropy, and a desire to understand that. And one thing that was understood very early is that actually you don't need to be quite so fancy. Even in the absence of gravity and in the absence of a black hole, you have a very similar effect, which is called the Unruh Effect, which I'll discuss, which is the fact that basically as soon as you take a quantum field theory and cut it into parts, then any part of it will be in a mixed state, and in certain cases it'll be actually in a thermal state, just as black holes are thermal. And then people still wanted to understand what was going on. So this was something that they discovered about field theory. So Hawking's discovery was about quantum field theory in a black hole background. It wasn't really a quantum. He didn't do a quantum gravity calculation. Then they realized that the thermality that Hawking saw and the entropy he saw could be seen even in flat space. So quantum field theory in flat space. That's what these guys figured out. And then sort of picking up that idea and going back to the black hole, the question was whether the entropy could be associated to this entanglement. And so the idea of taking a field theory and just cutting it up and calculating S of A was invented independently by these guys. The question being whether the black hole entropy is entanglement entropy. And they discovered in particular that there's an area law for the entanglement entropy, meaning that there's a UV divergent contribution to S of A. The leading contribution is a UV divergent contribution proportional to the area of the entangling surface. And then these guys pushed forward the idea of computing entanglement entropy in quantum field theory, in particular, moving away from the question of black holes and just computing it for its own sake, and in particular pushing the calculational techniques in the context of 2D CFTs and getting much further along. And this, as far as I understand, is where it entered condensed matter physics and became a popular thing, or one of the ways in which condensed matter physicists became aware of how interesting a quantity this is through the work of Calabrese and Cardy. And then another milestone within high energy theory is the Ryu-Takayanagi formula from '06, which brings in holography, holographic entanglement entropy. And then, of course, there's enormous developments since then, obviously. Okay, so let me explain a little bit more the scope of these lectures. I mean, there's obviously a huge amount to be said on this topic, and I'm only going to scratch the surface, but I wanted to try to do it saying things a little bit concretely, as opposed to just, you know, giving a lot of pictures or something. So to try to be as concrete as possible, I wanted to limit the scope. So in this, in these lectures, I'm going to limit myself, first of all, to relativistic field theories, and we're going to use that fact. And then I'm also going to give myself a bit of an artificial restriction, which is I'm just going to consider a two-dimensional quantum field theory. So in 1 + 1, and actually just 1 + 1 Minkowski space. Okay, this restriction is just for basically for pedagogical purposes, and one can easily, many of the things I say, you will be able to, without a huge amount of effort, generalize to higher dimensions. Other things, it's very subtle, and there are new effects in higher dimensions, of course, as usual. Okay, so that's my scope. Okay, and of course, the main reason for this restriction is that I only know really how to draw things in 2 dimensions, so there'd be no point in my trying to go to higher dimensions. Okay, so we're ready to begin, unless there are already questions.
Maybe I'll ask one. So what's
Yeah.
the answer to the question whether black hole entropy is entanglement entropy or not?
Sort of. So in the way that it was originally conceived, not really. But there's sort of a more general sense in which, I mean, of course, well, one answer, of course, is, as David said in his last lecture, all entropy is entanglement entropy. And so in that sense, black hole entropy is entanglement entropy. But in the sense, if you ask what is the contribution to the black hole entropy of the quantum fields living on that background, it is very subleading. It accounts only for a small part of the full black hole entropy. Okay. So were there any other? I'm going to be using relativity. And there's a key concept in talking about entanglement entropies in relativity, which is to introduce time into the picture. So again, we're in 1 + 1 dimensional Minkowski space. But the entanglement entropy S of A is defined where A is a spatial region, again. So what is a spatial region? Well, it's just going to be, so there's not too much you can do. Let's say the time we're considering is at t = 0. Then what kinds of regions can we have? Well, we can just basically have an interval or some collection of intervals, okay? So our A will be maybe an interval. It could be disconnected. It could have multiple components and so on, okay? all of these components, if you have multiple components, have to sit on a single time slice. Okay, you're not allowed to have multiple components like this or something like that. That's not allowed. Okay. Now, let's consider some operator in A. So if I have some operator, how many different colors? Okay, so let's say I have an operator OA, which is in A, then the expectation value is, of course, determined simply by knowing simply by knowing rho sub A, right? But actually, let's say I have an operator which is a local operator, so local in space and time, but which is located not on A, so a priori O sub A could be here, but it could also be somewhere to the past or to the future of A, as long as it's close enough in time, by the Heisenberg equation of motion, it can be written in terms of operators, no longer a local operator, but I can evolve it in time using the Heisenberg equation of motion to the time slice where A lives. And if upon doing that, and in doing that, the operator will not spread faster than the speed of light, because this is a relativistic quantum field theory. And if in doing so it remains within A, then I can also compute its expectation value knowing rho sub A. And in particular, the operators for which that's true are the ones within this causal diamond. So this is called the causal domain or causal diamond of A. And for any operator so I'll call it D of A, in D of A, rho sub A tells us its expectation value for any operator O sub A. Okay, so that means, in particular, that rho sub A represents the state not just on A, but on D of A. And it means that S of A is associated not with A, but with D of A. In particular, it means that if I did a different time slice that looked, instead of being straight, but it looked like this, wait, let me do this. But it looked like this. That's another valid time slice. It's curved, but that's okay. The state for this time slice would also be rho sub A, and the entropy would still be S of A. Okay? So any time slice within this causal domain has the same rho sub A and the same S of A. Or if you want to work, so I've been implicitly working in the Heisenberg picture. If you want to work in the Schrodinger picture, the rho sub A's associated to these slices within D of A are unitarily related, and they all have the same entropy. Okay? So whether you work in Schrodinger or Heisenberg picture, that's true. Okay? So, so it's very important to consider not just, so when we're talking about a relativistic theory, we don't associate entropies with a region, but rather with causal domains. And if you want to be technical, what you would say is that the operators living within the causal domain form a subalgebra. Okay. So let's do an example. Whoops. Okay. There. Just juggle too many things to hold. Okay, so my example is going to be one of the simplest intervals you can take, which is just half the space. So I'm going to take A to be this whole half line. So t equals 0, x greater than or equal to 0. And the causal domain of this is this wedge here. And this wedge is called Rindler space. And it is basically absolute value t, absolute x greater than or equal to absolute value t. And furthermore, I'm going to consider, so again, I have some relativistic quantum field theory on this Minkowski space, and I'm going to restrict ourselves to the vacuum. The reason being that the vacuum is special because it is the only state that's invariant under the full Poincare group. Okay? So I'm going to use the invariance under the Poincare group. So we're going to take rho is this state. Okay? And this is a very simple case where it's simple enough that we're actually going to be able to write down an expression for rho sub A and evaluate S of A quite generally. Okay? So that's why it's interesting. And this is also kind of the first case that was well understood. And what Unruh understood is that I don't think he said it in these terms, but because this half of the space is entangled with this half of the space, if we trace out this half and are left with this half, we're left with a mixed state. And so for an observer who stays within the causal domain of A, the world is in a mixed state, even though truly the world is in a pure state, but that observer can't tell, can't make the necessary observations to know that the world is in a pure state. So as far as that observer is concerned, the world is in a mixed state. So what's an example of an observer who stays within the Rindler space? So not a anybody who's stationary or moving at a constant velocity will enter and leave Rindler space, if they enter it at all. So the only way to stay within Rindler space is to always keep accelerating. And so Unruh studied the physics observed by an observer who undergoes a constant acceleration. If you undergo a constant acceleration, you'll follow a hyperbolic orbit, and you will stay within Rindler space. And what he showed is that for such an observer, not only is the world in a mixed state, but the world is actually in a thermal state. Okay? Such an observer observes a thermal bath of particles, even though actually the system is in the ground state. Okay, so let's see if we can understand that. And so another reason I want to talk about it is that to understand that, I mean, there are of course different points of view, but the technique using Euclidean path integrals is quite general and powerful. So I want to go through that. Okay, so we want to compute rho of A using Euclidean path integral. Okay, so rho is this state. So the first thing we need is a path integral representation of the ground state. So we're going to work in a position basis, meaning so we have some fields, and we're just going to take the field values as our basis. So we have some 5x. These are the field values. And this is, whoops. So this is some, for a given phi, for a given function phi of x, this is one of the basis vectors. And we can represent in this basis the ground state by a path integral as follows. So we do a path integral on the half space. This is x. Well, I guess it goes this way, but anyway. This is Euclidean time, tau, where we put as a boundary condition phi equals the given phi of x. This phi, actually, let me put a label. So yeah, let me be a little more precise. So phi at tau equals 0 is the given phi naught of x. And this is how you compute the ground state wave functional in this position basis, position meaning field value basis, using a Euclidean path integral. And actually, I should have, there's some overall normalization that we don't really care about. OK, so that's our ground state wave functional. And now what we want to represent actually is not this, but rather the operator rho. So that's an operator, so we need a some matrix element. So we have phi naught of x rho phi 1 of x. And that's, of course, that actually just factorizes. It's kind of boring. And so what is this? Well, we already calculated this thing. It's this path integral. So again, this is our Euclidean time tau. And we put a boundary condition that phi at tau equals 0 minus is phi naught of x. And then we have another thing here, another half space with a different boundary condition that here phi on tau equals 0 plus. So this is 0 minus 0 plus is equal to phi 1 of x. So now we have this funny, so we're calculating just a product here, and we have this funny path integral where we've just taken our Euclidean space and just taken scissors, cut it along tau equals 0, and on one boundary we put this these field values. On the other boundary we put these field values, and then we do the path integral. Okay. Now we need to take a trace. So the next thing we need to do is, I guess my formula disappeared, but we need to take a trace on a complement. And the trace means we just integrate over everything. So we want, yeah. So let me write this. So rho sub a is trace on a complement rho. And that means it's the integral on phi of x on a complement of rho of so in other words, on a complement, so here we have A. And on a complement, we put an arbitrary field on the top and the bottom, but the same one, and then we integrate over that. So that's the same as just gluing these back together. So the picture you end up with is that you have the full, so let me draw it like this. So we again have 0 plus 0 minus. And again here, so again, a matrix element for rho sub a is going to be phi 0 on a of x, rho sub a phi 1 on a of x. It's going to be given by the following path integral, where I put a boundary condition phi 1a of x, phi 0a of x. And everywhere else, I just do my path integral. Okay? So this is a path integral on the Euclidean plane with a funny, where I've done a cut from x equals 0 out to infinity, and I've put a certain boundary condition on the bottom of the cut, some other boundary condition on the top of the cut. Those are my boundary conditions. And then I do the path integral, and that tells me this matrix element. Okay? Yeah? Yeah, so I didn't explain that, but indeed, one way to think about this is, you can represent the operator e to the minus beta h as a path integral, Euclidean path integral over Euclidean time interval of length beta. And now we're doing that and taking beta to infinity. And so we end up with a half space. Okay? So in fact, if one were interested in doing the same calculation but at finite temperature, you can, it goes through the same way and so on. You just have to keep track of that now this is a cylinder instead of being a plane and so on. Okay. Any other questions? Okay, so now we have this path integral representation of the reduced density matrix. And now we just kind of look at it again, and we realize that actually this thing, if you think of it as an operator relating the state on the bottom of the cut to the state on the top of the cut, one way to think about it is just like this. But so here, in fact, yeah, this is good. So how did this come about without going through all the whole long story about Euclidean path integrals? Basically, H is the generator of time translations, right? And here we're doing it, so it would normally be e to the minus I t h. But since we're doing a time translation in Euclidean time, the it becomes beta, and so we get a translation in Euclidean time by beta. And here we get a Euclidean rotation through an angle 2 pi. So this operator, rho sub a, so this implies that rho sub a is e to the minus 2 pi times k, where k is the generator of Euclidean rotations, which is the same as the generator of boosts. So here I have a boost symmetry which acts within Rindler space, which preserves Rindler space, which does like this. Okay? And K is the generator of the boost symmetry. So K is an operator that acts within A. Okay? It acts on the A part of the Hilbert space. And in fact, we can write a formula for it because the boost symmetry is very simple. We can write it because it's a diffeomorphism. We can write it in terms of the stress tensor. It's some geometric operation, some local geometric operation. So we can write it in terms of the stress tensor. And the formula is very simple. It's just an integrated energy. But where if you look at the magnitude of these things, they become larger out here and smaller out here because it's kind of like a rotation. So the energy would have been this. Whoops. So this is a formula for the energy. We don't have the energy. We have the boost generator. And so you have multiplied by x. And the integral is only from 0 to infinity. So we have quite an explicit formula. And so we see that, in fact, rho sub a, so rho sub a is thermal. It's a thermal state, but not with respect to the usual Hamiltonian, but with respect to K. Which explains why an observer whose trajectory is simply given by boosting, that's one of these accelerated observers, basically their trajectory is obtained by just acting with a boost on some initial position. That observer is, for the purposes of K, stationary, just sitting there. And that observer observes a world which is in thermal equilibrium. Okay? At what temperature? Well, at a temperature 1 over 2 pi. So more precisely, the I mean, 1 over 2 pi with respect to k. Okay, so what does that translate into in terms of a physical temperature? Well, you have to look at this. There's an x factor multiplying the energy. So by the way, this, I hope, I should have said, this operator is just the energy density operator. Maybe, sometimes it would be written like a curly h or something. So that's gotten multiplied by x. So let me write. For an observer at a proper distance L, which is square root of x squared minus t squared, so a given proper distance L, from the origin sees a local temperature 1 over 2 pi L. So if you're wondering where are the units here, L is a distance, and so, or a time, so we get a temperature by taking its inverse. So that means that the fields near the entangling surface, which is the origin here, this is my entangling surface, dA, just a point, fields near dA are very hot. They're hot because they got massively decohered, because they're highly entangled with what's out here. So the closer you are to the entangling surface, the more entangled you are. Basically, if you think about like the modes, there are more modes that are entangled with, or that lead to entanglement between A and its complement close to the entangling surface, and so more of them got decohered, and so the temperature is higher. That's kind of the intuitive way to think about the temperature of Rindler space. And what Unruh showed is that indeed an observer who stays at fixed L, so one of these trajectories has constant L, carrying a particle detector, will see a thermal spectrum with precisely this temperature. Okay? That's the Unruh effect. Okay, and we can use this to estimate the entropy. So here I want to emphasize that sometimes entanglement entropy, because it sounds fancy, sounds like it's not a regular entropy. It's just a regular entropy. It's a very physical thing. And let me not erase that. And so what we want is just to consider the total entropy by adding up the local entropies. Okay? So let me actually say one thing here that might be a little confusing. So you might be confused by the statement that this system is in thermal equilibrium given that it has a temperature gradient. So the temperature is position dependent. The effective local temperature is position dependent. You can say, well, by definition, that's not, isn't there going to be transport of energy and so on? But that is precisely counteracted by the fact that we're in an accelerating frame. So in this accelerating frame, the effects of the acceleration are exactly counteracted by the fact that there's a temperature gradient, and indeed the full thing is in perfect thermal equilibrium. Okay? So now we're going to estimate S of A simply by adding up the entropies along A. So estimate S of A. And let's say we have, just to keep it simple, we have some massive field for a field of mass M. And so a field of mass M has an entropy density as a function of temperature, which is basically like this, in 1 + 1 dimensions. If the temperature is above the mass, then it's proportional to the temperature. If it's below the mass, it's 0. That's my approximation. So I better make it clear that's an approximation. So T for T greater than m, 0 for T less than m. If the temperature is below the mass, the field is frozen out. It's not excited, no entropy. If it's above the mass, the field is effectively massless. For a massless field, the entropy has to be proportional to the temperature because there's nothing else. Okay? Nice approximation. So we're just going to use this to, and then we're going to just add up the entropy density along this line to 0. Okay? So S of A is basically integral from 0 to infinity dx little s of t, where t, again, is 1 over 2 pi x. And so this thing is the integral from 0 up to the place where t is equal to m, which is basically 1 over m. So once you get past, this is 1 over m. In here, the fields are excited, and out here, they're frozen out. Dx 1 over x, leaving out 2 pi's and stuff like that. Well, this thing is divergent, so we better cut it off. So the first thing we learn, so we've already learned something, is that the entropy is infinite. Okay? So we better cut it off. It's UV divergent. So we're going to cut it off at some epsilon here. I'm sorry, my diagram has become rather busy. Some UV cutoff scale epsilon. And then we get minus log epsilon. So it's logarithmically divergent with respect to the UV cutoff scale. And of course, there's some constants here and stuff like that. Multiplicative constants, additive constant. What's that? Thank you. Yes, it's good to take the log of a dimensionless number. Exactly. Okay, so that is basically the entropy of Rindler space for a massive field. Yes, homework problem. Homework problem is, which is not hard at all. Generalize this very crude estimate to higher dimensions. So you have to, this gets changed and the integral gets changed, okay? And you should find that area law that I promised you. Any questions before I move on? Now here, this this calculation wasn't overly precise. I want to be a little precise, but still keep it sort of under control. And so the next example is going to be, I'm going to impose more symmetry, namely conformal symmetry. Now, when we have conformal symmetry, the mass has gone to 0. And so now, in addition to the UV divergence, if I take m to 0, I get an IR divergence. And that's from the fact that this 1 over m has now gone off to infinity. So now, not just the fields within this little interval are entangled, but they're all entangled. So we need to cut that off. So to cut that off, we're going to, instead of dealing with the half space, we're just going to deal with a finite interval. Okay? And we're still going to be in the vacuum at first. Okay. So here is our one interval. And let's say it has length L. Okay. And now well, this calculation, okay, so first of all, I can be a little more precise here. So the entropy density in a CFT as a function of the temperature, you can compute it, and you get this. It's proportional to T, as I said before. It's also proportional to the central charge. Okay, and this is an exact formula. This is not some crude approximation. This is just a fact about CFTs, that the entropy density is 2 pi c over 6 times the temperature. Now I'm going to plug that in here and do the same calculation, but just in the vicinity of one endpoint. So that implies that the UV divergent part of S of A from one endpoint is equal to, and here I wasn't super careful, so let me put the 2 pi back in. The temperature is 1 over 2 pi L. So, so including that, you just get C over 6 log epsilon, log 1 over epsilon. Now we have 2 endpoints. That means, so this whole thing from 2 endpoints is C over 3 log 1 over epsilon. Now, of course, the entropy is I mean, this log here is not too happy because its argument is dimensionful. We know that the entropy is dimensionless. What other scale do we have? It's a CFT. The only other scale we have is the length of the interval. So that gives us this formula, S of A equals C over 3 log L over epsilon. Okay, I need something with dimensions of length to absorb the epsilon. The only thing is L, and so I get this. Okay? Now, this was a bit fake because how did I get this entropy? I got it by adding up local entropies. And you could say, well, the state is not really like that. I mean, that's just, you know, you can't, the entropy is not a local quantity in a general state. You can't get the entropy just by adding up some local entropy densities. So if you don't believe this calculation, you can obtain this honestly by Euclidean path integral calculation, and similar to the one I sketched, just more complicated, and then you have to use some CFT technology. It's not too complicated, and indeed you get this. Okay, so that's what Holsey, Larson, and Wilczek and Calabrese and Cardy did. So we have this C over 3 log L over epsilon. And I am told that this formula has some important applications in condensed matter physics, but since I'm not an expert on that, I'll skip it. But I mean, I will say, I mean, we're going to see a couple field theory applications in a second, but if you had some way of computing, like if you had some field theory and you didn't know whether it was a CFT, and you didn't know if it was a CFT what its central charge was, but you had some way of computing the entropy, you could see whether you could fit your data to this formula, and if you could, then you could extract what the central charge is. So that's kind of one way to think about this formula. Now, without too much trouble, one can generalize this formula to the case where the full system was not in the ground state. So far, this was, again, in the vacuum. But let's say where the full system is at some non-zero temperature, let me call it T naught, then in your Euclidean path integral, you have to basically, instead of the path integral being starting out life on the plane, it starts out life on a cylinder where the Euclidean time direction has circumference 1 over T naught. And then you go and you do the same CFT stuff, and you get the following answer for the entropy. So it starts out C over 3 log, and then there's a cinch. Okay, and I don't know how fast you are at reading these formulas and figuring out the behavior at small and large L, so I'll do it for you. At small L compared to 1 over T naught, cinch becomes just pi T naught L, then the pi T naughts cancel. And so that's what you would expect. I mean, there's some thermal length 1 over T, because remember, we're in a CFT, so there's no other lengths. So when L is small compared to 1 over T naught, then it doesn't really know it's at finite temperature, and so it just looks like the log that we had. But on the other hand, when L is large compared to 1 over T naught, then you get log cinch, and log cinch is basically linear, and so it turns over to something linear. And what is this linear thing? Well, now the interval is very large, and we get basically the kind of thing that David was talking about in the last lecture, where you simply get the thermal entropy density, which is just proportional to L. And indeed, what is the thermal entropy density? It's 2 pi c over 6t. And that's exactly what you see here, because you get pi t naught c over 3. Okay? So linear just from thermal entropy density. In addition to the contribution, of course, there's still a log epsilon divergence. So in addition, you get the divergent contributions from the endpoints. Okay? So it's all quite reasonable looking. Any questions? Okay, so one can do a lot more in a CFT, but I'm going to move on to a general two-dimensional theory. So again, just one interval in a general theory or a massive theory if you want. So in a massive theory, so what you expect based on our discussion, let me draw it like this. So here's x. I'm not going to draw the time direction. Now you have this scale, which is the correlation length, 1 over the mass. And if the region is much larger, is much larger than the correlation length, let's say this is the correlation length, which is 1 over the mass, then you basically expect from our Rindler discussion that the fields further than 1 over m away from each endpoint basically don't contribute. They're not entangled anymore with a complement. And so you expect this rising thing to saturate, okay? And let me actually to avoid confusion, so for now I'm going to be, again, in the vacuum. But anyway, so what you expect, so you expect S of A to saturate at L like 1 over M. So it should look something like this. Comes up and then saturates. And indeed, you can try to compute this. So now let me say something that David alluded to in the last lecture. One of the dirty secrets of this subject is that even though these are very fascinating quantities, very rich and tell us a lot about the physics, they're actually incredibly difficult to compute in practice. And so this quantity, so I'm just talking about the entropy of a single interval in a free massive theory, was computed using a combination of analytic and numerical techniques for free fermions, free massive fermions, and free massive bosons by Cassini and Huerta, and basically they got, curves like this, okay? Now you might notice one thing about everything we've seen so far. As a function of L, so we have log L, we have this complicated looking thing, which looks like this, we have this. Two things about these functions. They're all increasing and they're all concave. The fact that they're all increasing is because I'm on an infinite line. So just as in David's lecture, had I put my theory on a circle, all of these things would go up and then come down again. So the fact that it's increasing is just because of this very simple geometry I've chosen. The fact that it's always concave, however, is always going to be true, and that's because of strong subadditivity, a general property of entropies. So strong subadditivity is the following inequality that if I have disjoint regions, not necessarily separated, but they could be next to each other or not next to each other, then we have the following inequality. So this is just a fact about quantum mechanics, has nothing to do with quantum field theory. Okay, but now in particular, if we can compute the second derivative of S by making A and C. Let me okay, let me not do that. By making A and C infinitesimal, and then you see that the difference is basically the second derivative of S. Okay, because we have like S of BC minus S of B, that's a first derivative, and S of AB minus S of ABC, that's a first derivative, and then we're taking the difference of those, so it's a second derivative. Okay? So the second derivative by virtue of this inequality is always negative. Okay? I have 10 minutes left, or I'm done? I have 10 minutes left. Okay. So now it turns out you can get a lot more mileage out of strong subadditivity than the concavity. So this is something that was understood in 2003 or 4 by Cassini and Huerta. So let me explain this now. So what we're going to do is we're going to take this inequality and we're going to combine it with relativity. Okay? So, and we're going to show that it implies something much stronger. So we're going to consider the following. So you see this configuration of A, B, and C? These are all at the same time. But now let's add the time direction. And so I can't just have A, B, and C sort of randomly arranged in time, because I want them all to be on a common time slice. However, that common time slice does not have to be constant time. It can be curved as long as it's an honest time slice. So I'm going to choose it to look like this. So here's A, B, and C, where these are null. A and C are null segments. Okay? I'm going to use the fact that because I'm in the vacuum is Lorentz invariant, so the entropy is only a function of the proper length of a given interval. Okay? So when I talk about S of AB, for example, here's AB looks like this, but I can also think about it. Remember that the entropy only depends on the causal domain. So I can think of AB as looking like this, and I can think of BC as looking like this, and ABC as just being this. And so the entropies that enter into this inequality are only functions of these four proper lengths. The proper length of B, proper length of ABC, of AB, and of AC, and of BC. And you can show that because I chose, it's a little exercise in Lorentzian geometry, because I chose A and C to be null, those lengths have the following property. LAB times LBC equals LB times LABC. It's not too hard, so I'll leave this as an exercise. Exercise, show this. That implies, so if I plug, okay, so if I think about the entropy as a function of log L, which I'm free to do. I mean, we know that it looks quite simple when written as a function of log L. So think of it as a function of log L, and then let me rewrite this a little bit. Log of this plus log of this equals log LB plus log LABC. Okay. That means that if I work in log space, then essentially it looks like this, right? Because B plus ABC equals AB plus BC. So I just rerun the same argument that I had before for the concavity, but in log space. Okay? So that means that S is concave in log space. Okay, by which I mean that the derivative, that the second derivative with respect to log L of S is negative. So let me define a function, capital C of L, which is 3 times the derivative, 3 times the derivative of S with respect to log L. Okay, implicitly in all of this, I'm using the fact that I'm in the ground state of a relativistic theory, and therefore the entropy for a single interval is just a function of the proper length of that interval. So I have the right. Normally, when you write S of A, and S of A can have some complicated geometry or topology or whatever, but here S is a function of one variable, capital L. So I don't have to write S of A, I can just write S of L. And I define this quantity. And then this is saying that C prime of L is negative. Now, what does C of L look like? This is very similar, actually, to what David was doing in the last lecture. So what does C of L look like if I happen to be in a CFT? Everything here is for a general relativistic quantum field theory. But if I happen to be in a CFT, then I know that S is just log L, C over 3 log L. So for a CFT, capital C is a constant little c. But that means that if what my theory is doing is it's an RG flow connecting a UV fixed point to an IR fixed point, when L is very small, the entropy will be that of the UV fixed point. And when L is very large, the entropy will be that of the IR fixed point. And therefore, this function will interpolate between the UV value of C and the IR value of C. So if I have L, capital C of L, it'll go from C of the UV fixed point down to C of the IR fixed point. And the theorem tells us that in between it has to decrease. And so this is the C theorem, proven using strong subadditivity and relativity. So this theorem, the C theorem, which is that CIR is less than or equal to CUV, was originally proven in the 80s using two-point functions of the stress tensor by Zamolodchikov. And what's interesting is that the ingredients in Zamolodchikov's proof are relativity and unitarity. And the ingredients here are relativity and unitarity as expressed in strong subadditivity. And so the ingredients are the same, but the method of proof looks totally different. The interpolating C function is different. They both decrease, and they have the same values at the endpoints, but in between they're not necessarily the same. And so we have a totally different proof of the same fact. OK, and I think I'm out of time, so I'll stop there. Yeah.
That's only at 0 temperature. As soon as you're non-zero temperature, this doesn't apply?
If you're at non-zero temperature, it does not apply. I don't know if there are known counterexamples. I actually don't know, but certainly the proof breaks down for sure.
So what in this is unique to 1 + 1 in this proof?
So the whole structure, is at first glance is all 1 + 1. Like this diagram is definitely in 1 + 1. Now, if you try to generalize it, then you have to figure out, well, what kind of regions am I going to use? Like you could use like a strip or something. It turns out that doesn't give the result you would want, although it seems like a reasonable guess. What does work in higher dimensions is to use disks or balls. And then your job becomes much more complicated because you don't have such a simple diagram anymore. When you intersect two balls, you don't get a ball. You get some weird oval shape, lentil shape thing. And so Cassini and Huerta did generalize this to 2 + 1 dimensions. And that is the F theorem. And Cassini and collaborators very recently generalized it to 4 dimensions and thereby got a proof of the so-called A theorem. So these are all statements basically of this form where you have some number characterizing the IR and UV fixed points. In the case of 2 + 1 dimensions, this F theorem proven by entropic methods is the only known such constraint. In 4 dimensions, the A theorem was previously known and proven using more conventional field theory techniques. No such constraints are known in higher than 4 dimensions. And the proofs get more and more complicated. So it's really not clear what's going on in higher dimensions.
So here you have a system. The system is infinite and the cut is of n, right?
Yeah.
So what is setting the scale at
So I'm considering, so of course this is for some RG flow from a UV to an IR fixed point, and such an RG flow has a characteristic scale to it. For example, a very simple example of an RG flow would be if you have a massive theory, at very high energies, effectively the mass is 0, and so that's a fixed point. At low energies, it's gapped out, so you have nothing. You have a trivial theory, and the scale at which that transition happens is 1 over the mass, the Compton wavelength of the field. So any RG flow has a characteristic scale at which it goes from looking like the UV fixed point to looking like the IR fixed point. No. So this.
Can you repeat that question?
Yeah. So as I understood it, so he was asking about this. You're asking about this equation? Yeah. This equation is for CFT. And so it's valid here, and it's valid here, with different values of the coefficient little c. It's not valid in between. In between, you get some complicated thing. Okay? For example, you can apply this, take this, and plug it into here, and you'll find a curve that looks like this, except it just drops to 0. Right? Out here, the first derivative is 0. The s d log L is 0. And so your curve just drops to 0 because in the deep infrared, you have nothing. Okay? So that's a simple example. But what it would look like if you made a transition instead of to a trivial theory to a non-trivial theory is that at long distances, you would have another log, but the log would have a different coefficient from in here.
The subtlety you mentioned about factorizing the Hilbert spaces, is that true for any theory? Is it just for, does that emerge from just gauge theories, for example?
It depends basically how fancy you want to be. So it obviously occurs for gauge theories. For gauge theories, the Hilbert space obviously doesn't factorize because you have these operators like Wilson loops. Another way to say it is because of the Gauss law constraint, the physical Hilbert space is smaller than the Hilbert space you get by taking a tensor product. Now, if you want to be more sophisticated and do quantum field theory in an algebraic way, where everything is mathematically well-defined, then there's never Hilbert spaces associated to regions in the first place. There's just algebras of observables, and so it's all done in the language of von Neumann algebras, and so on. And so from that point of view, so if you think even about a scalar field theory hard enough, at first glance, a scalar field theory looks like it should factorize. But if you think about it hard enough, and if you really insist on being in the continuum, so you don't take a condensed matter. Condensed matter theorists absolutely do not care about this question at all. I mean, they will refuse to talk about this question because everything was a lattice, and so obviously the Hilbert space factorizes. Even the gauge fields are emergent, and so even for gauge fields, there's no problem at all. Okay? But if you say, no, 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 I'm a field theorist, I work in the continuum, there's no lattice, then even a scalar field has this problem. Even a scalar field is not factorized because along the entangling surface, you have continuity of the field, which tells you the inside and the outside are not unrelated. So you can definitely have a lively debate about whether this is an issue or a non-issue or whatever.
Even in condensed matter, if you just look at free fermions on the lattice, the Hilbert space of free fermions doesn't, just of fermions doesn't factorize, but it's a little bit easier.
Oh, no, 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 the issue with fermions, I think I disagree with that. I think just by being a little bit more careful about your definition of the operators, the Hilbert, you have to include cocycles in your definition of the operators, and then the Hilbert space factorizes.
I'm not saying it's isomorphic to a factor, but if you start from the kind of naive degrees of freedom, it's not.
Yeah, but that problem is kind of easily fixable. Yeah.
We'll let the instructors argue while we take a 5-minute break.